Hello guys, so you're welcome to this lecture. We want to start off with hyperbolic equations in 1D. This will take us a while. Once we are done with that, we'll move on to elliptic equations. So the outline will be that I'll go through an introduction of a few things that we've already covered, okay, in the initial part of the course. We'll look at a model problem and how you can tackle that using the method of characteristics. And then we'll look at how you deal with it using the finite difference methods. We'll look at simple explicit schemes, especially the upwind scheme. We'll say some things about the CFL condition, Fourier analysis of the damping and dispersion of the solutions. And then apart from the upwind scheme, you also have the Lax-Winthrop and the Lipfrost schemes that we'll briefly mention. Okay. So this is going to be a short lecture. So here initially when we look at the classifications of PDEs, we said that you can consider a PDE second order of this form where the solution phi there is unknown, that's a dependent variable, and A, B, C, D, E, F, and G here known constants, or they are variables of x, y, and phi. Okay, so the solution of the PDE of this form, that phi that you compute, is a surface. Okay, it's a surface in space, and that surface consists of various space curves known as characteristics curves. Okay, now there are curves where the second order derivatives, the second derivatives of phi, right, are indeterminate. That is, they are not uniquely determined. Okay, those curves along the surfaces. So if a characteristic curve, say y equals y is a function of x, exists, then the slope can be given by this relation here, equation 2. Okay, so this is very important. You can often use this to help you describe single second order PDEs of this form. Okay, so once you have your equation of this form, the discriminant, which is b squared minus 4ac, will often help you to tell whether the equation is hyperbolic, elliptic, or parabolic. Okay, so if the discriminant b squared minus 4ac is greater than 0, then you have a hyperbolic PDE. Okay, so we'll look at that. It's parabolic if it's equal to 0, and it's elliptic if it's less than 0. So here we just want to concentrate on the hyperbolic case. So an example is the wave equation, which is d squared u, the t squared is equal to c squared, d squared u dx squared. So if you put this in this form here, right, in the form of equation 1, you will see that dt dx, where t here is your y, dt dx is equal to 1 plus or minus 1 over c, and so you get these characteristic lines. So you have two characteristics as this says. So this is just a simple example to illustrate the equation there. Okay. Again, when we're looking at the classification of PDEs, we said that that wave equation can actually be solved, and the general solution is given by this. So this is basically two waves, right? One propagating to the left, and the other moving to the right. Right, and which is consistent with the idea that you have two characteristics, one of them moving to the right hand side and the other is moving to the left hand side. Okay, the A here should be C actually, to be consistent with this. Okay, good. We also learned that for hyperbolic equations, all right, signals will often move with finite speed, okay, along the curves known as the characteristics. And that brings us to the idea of a domain of dependence and the domain of influence, which we discussed before. In other words, if a signal starts from here, all right, it will influence whatever is here, right? The signal is moving along these characteristics. And on the other hand, if whatever is here, if you like, depends on information that is coming from this path, known as the domain of dependence. Okay. So we've looked at this before, so you can go back and look at the initial stuff on classification of PDEs. All right. So basically, that is a short introduction to the hyperbolic PDEs. These ideas, introductory ideas, will carry them forward as we move forward to talk about more interesting advanced stuff. Okay, so in the next lecture, we'll look at a model problem as we've been doing and see how we can use the method of characteristics to understand the solutions to the model problem, the simple model problem. Once we are done with that, we'll move on to using the finite difference approach to dealing with that. Okay, so in the next lecture, we'll look at the model problem and the method of characteristics. Okay.